This video is part 3 of chapter 2. We're going to discuss the topics of finding quartiles and constructing box plots. We'll also learn how to analyze a box plot and learn if some data is left skewed, right skewed, just by looking at a box plot. Let's start with quartiles. So what is a quartile? A quartile is a statistical term that describes the division of observations into 4 intervals or quarters. We're going to need 3 numbers. The first number is Q1, which is the first quartile. This is a number in the data where 25% of the data fall below the value and 75% of the data is above the value. We've seen the median before. This is also known as Q2, or the second quartile. This number is the number that's right in the middle of all of the data. So 50% of the data is below this value and 50% is above this value. Then there's Q3, or the third quartile. That's when 75% of the data lives below this value and 25% of the data lives above this value. Notice I have a little rectangle here, and what I can do is I can think of this rectangle as data. And imagine that we have organized this data from smallest to largest. So I want to think of the data as this rectangle. And if I cut the rectangle in half, that's like finding the median of the data. That would mean half of the rectangle is to the left and half is to the right. Now I can think of the left half of the rectangle and think about cutting that into half. And if you do that, that's quartile 1. And then I can think of the right, to the right of the median, there's this rectangle. I can cut that into half, and that's quartile 3. And so these 3 numbers divide this large rectangle into 4 pieces. So quartile 1, as you can see, 1 rectangle is to the left and 3 rectangles is to the right. In other words, 25% is to the left or below that value, and 75% is above that value. With quartile 3, we have 3 rectangles to the left, which would mean 75% of the values will be less than quartile 3, and we would have 25% of the values above quartile 3. Another important statistical term is the interquartile range, or IQR. Now, we've talked about range before, and we said range is the difference between the maximum and minimum values. Well, the interquartile range is the difference between quartile 3 and quartile 1. So if we take whatever our value is for quartile 3 and we subtract quartile 1, that will give us the middle 50% of data, how spread out that middle 50% of the data is. Now I want to mention box plots, which are graphs that summarize observations of a variable. 5 statistics are important when we try to construct a box plot. We usually call these 5 statistics the 5-number summary. So when I want to build a box plot, I need to keep in mind these 5 numbers. The first number is the minimum value. The second number is the first quartile. The third number is the median. The fourth number is the third quartile. And the fifth number is the maximum value. If I can find these 5 numbers, that will help me build a box plot. In the next slide, I will show you how to take some data and build a box plot and what each part of the box plot represents. Now, box plots are useful because they provide a visual summary of data that helps researchers quickly identify the median, how the data is dispersed, and it also gives signs if the data is skewed or not. That means, do we have left skewed data, right skewed data? Is our data symmetric? We can see all of this from a box plot. Here we have some data that we've seen before. This is a random sample of 25 college students, and these college students were asked how many hours per week do they typically work outside the home. So each number represents the number of hours a particular student worked outside of the home. Now, I want to find the 5-number summary, and I want to construct a box plot of this data. So the first thing I'm going to do is I'm going to sort the data from largest to smallest. So in a spreadsheet, I'm going to do that. I'm going to put all of this data into a column, and I'm going to sort from largest to smallest. It doesn't really matter if you do smallest to largest or largest to smallest, but I'm going to do largest to smallest. So I went and entered all that data into a spreadsheet, into one column, and then I asked the computer to sort the data. And probably you can see in the original data, the largest value was 40, and it's at the top of this, this column here, and the smallest value is 0. So let's construct that 5-number summary and also a box plot of the data. Okay, so let's start with the max. The 5-number summary, we said we needed to find the minimum and the maximum. So the minimum is the smallest data value in the set, and that's 0, and the maximum is the greatest, which is 40. We also need to find the median, quartile 1, and quartile 3. So we had 25 pieces of data. To find the median, we take 25 and add 1, that's 26. Then divide by 2, we get 13. So the 13th piece of data is the median. This is also the quartile 2, because that quartile 2 is 50% is above and 50% is below. Now you can also ask a spreadsheet to calculate the median for you. And we've seen that in the lab video we had last week. Okay, the next thing I want to do is I want to find one of the quartiles. I'm going to find quartile 1. So how I find quartile 1 is where the median is. I'm going to cover with my hand the upper part of the column, including the median. So where it says 14, I'm going to find the middle value between 14 and 25. And because this is an even amount of data, the median is going to be halfway between 19 and 20. And you can just count underneath so where that line is, I have 1, 2, 3, 4, 5, 6 pieces of data. And above that line, I have 1, 2, 3, 4, 5, 6 pieces of data until I reach the median. So separating everything below the median right in half. And this one is quartile 1 because it's on the lower side of the data. Quartile 3 is where the larger numbers are. So I'm going to do exactly the same thing where the number 13 is, the 13th row, where I've circled the median, 25. I'm going to look above that and separate that data in half. And where I separate it is between rows 6 and 7. The average would be 30. So here's the 5-number summary. The minimum is 0. The maximum is 40. The first quartile is 15. That's the lower part of the data. The median is 25, and the third quartile is 30. And to find these quartiles, remember that we're taking those two data values, like for quartile 3, I'm taking 30 plus 30 and dividing it in half, and I'm just getting 30. Now let's talk about how the data is spread in between the quartiles. So look at the top, so between quartile 3 and the maximum value. Notice that quartile 3 is the number 30, and the maximum is 40. So there's a range of 10 units between quartile 3 and the maximum value. While between the median and the quartile 3, the median is 25 and quartile 3 is 30, so there's only a difference of 5 units. So that data is less spread out than the top one. And then if you do the same thing between median and quartile 1, you'll get a range of 10 units. And between quartile 1 and the mean, you'll get a range of 15 units. So we can see that of all of these ranges, the range between the median and quartile 3 has the least spread, like the least spread out there, while the range between the minimum and quartile 1 is the most spread out. I'm going to start building a box plot now. So let me tell you the important parts of a box plot. First off, we see this orange square, and you can choose whatever color you want for the box plot. But really, we're focusing on this square with this line in the middle. And the line in the middle represents the median. Notice that line is right at 25. Then the bottom of the box is quartile 1. We see that quartile 1 is 15, and we also see that quartile 3 is 30. So this box shows us where quartile 1, quartile 2, and quartile 3 are. So the line in the middle is the median. And you can also see that this box is showing you the spread of the data. We said between the median and quartile 3, there's only a distance of 5 units. And so you can see where the middle line is in the box, the spread between that middle line and the top of the box. That distance is smaller than between quartile 1 and the median. Now the whisker part doesn't necessarily go to the minimum and the maximum. So what you have to do to figure out how long your whiskers are is we have to find the interquartile range. So remember, the interquartile range is where we take Q3 and subtract Q1. Q3 is 30, Q1 is 15, and if I subtract those two, I'll get this 15. Now, to figure out how long my whiskers are, I'm going to take 15 and I'm going to multiply it by 1.5. And I'll have this listed on the next slide. But right now, just listen to what you do. You take 15 and multiply it by 1.5. That will give you 22.5. And so the next step is to take 22.5 and add it to quartile 3. So quartile 3 is 30, and if I add it to quartile 3, I'll get 52.5. And if I take that whisker length and subtract it from quartile 1, I will get negative 7.5 because I'll take 15 and minus 22.5. So what this is doing, the whiskers are telling you where there would be, if you have data that lives outside the whiskers, you would have outliers. So our data, the minimum value is 0. And because the bottom whisker goes down to negative 7.5, there's no data in the negatives. So we would take that whisker and send it all the way down to 0, but no further. There's no reason to extend it further because there's no data. Our smallest data is 0. Okay, and our highest data is 40. So although we got our top whisker can go out to 52.5, we wouldn't go all the way to 52.5. We would stop it at 40 because that's where the last data set is. So what these whiskers tell you is we don't have any outliers in this data. Outliers are pieces of data that are very different from the rest of the data. And so if our whiskers, let's say we had a data value that was 70. Let's say our maximum was 70, and that our top whisker went to 52.5. Then we would have a dot outside of this box and whisker graph. So my whisker would go all the way to 52.5, and then I'd have a dot above it at 70. And that would tell me, hey, you have an outlier. You have a piece of data that's very different than the rest. So these whiskers are telling you where the data is similar and where things start to become very strange. And that is when we take the IQR and multiply by 1.5. I'm going to go back a couple of slides because I showed you a box plot. So let me just go back real quick. Here we go. There's this box plot that has these whiskers, and then it has some dots above it. And all of these dots are outside of the whiskers, which are telling you that you have outliers. Now, sometimes a box plot is shown vertically like this, and sometimes it's horizontal, like it's flipped on its side. And when it's flipped on its side, when we have outliers, remember that pulls the mean to the in the direction of the outliers. We could have the outliers below the box plot, or we could have it above it. And if we rotated this box plot, that means we could have outliers to the right or to the left. And those outliers are telling you if your data is skewed or not. We'll see some more examples in a bit. But for right now, I just want you to understand that the whiskers tell you where data is similar, and then you have, if you have points outside the whiskers, and you would have a point for each outlier, so something living outside the whisker length. So let's go back. Okay. Now, here was the formula for how to find your whiskers. Whiskers can extend up to 1.5 times the IQR away from the quartiles. So the maximum upper whisker reach is where we take quartile 3 and we add 1.5 times the IQR. While the minimum, where the lower whisker goes, is taking quartile 1 and subtracting that 1.5 times the IQR. An outlier is an observation that appears extreme to the rest of the data, and any data beyond the reach of the whiskers are considered outliers. So here's another picture of a box plot. And in this box plot, if I was to ask you how many outliers there are, you would say there's 2 because they are outside the whiskers of the box plot. So I want to mention the term robust statistics. So robust statistics are statistics that aren't heavily influenced by extreme observations in the data. Robust statistics allow researchers to better analyze data and draw trustworthy conclusions when data contains anomalies or abnormalities. So we mentioned earlier in chapter 2 that when we have numerical data and the numerical data doesn't have outliers, maybe it's symmetric, we usually use the mean to find the average of that numerical data, and we use standard deviation to describe the range, how things are dispersed. We could use the range to talk about the overall dispersion, and we can talk about standard deviation to kind of to mention how things are spread in the middle of the data. But the problem is when you start to have extreme data outliers, your mean and your standard deviation are really affected by these outliers. So when we have data that has outliers, instead of using the mean, we tend to use the median. Instead of using the range, we work with the IQR. And we don't tend to use standard deviation when we have a lot of outliers. We work with the IQR. That gives us a good understanding of how things are spread. So our robust statistics, the ones that aren't influenced as much by extreme observations, are the IQR and the median. And statistics that are influenced by extreme observations, and so you don't want to use them when you have really skewed data, are range, mean, and standard deviation. All right, here I have 3 graphs, 3 different histograms. So there's some data attached to each histogram. And I want to see what the box plots would look like for each one of these histograms. So let's focus on the one in the middle right now. So notice that this graph is symmetric, which means the mean is equal to the median, which is equal to the mode. So the median would be right in the middle of the graph. Well, it's not exactly perfectly symmetric, but it's pretty close, right? So you see that I have M in the middle that says median. So I would expect the median to be about there. And now if I was to think, so I have these bars, and remember that the bar height tells us how much a piece of data occurs. And so the higher the bars, the more data I have there. And so in the middle of the graph, I have a lot of data. And then you can see that I have less data going towards the ends. So if I was to split the median, if all of the bars were the same height, the the distance from the median to quartile one to from quartile one to the minimum, and from median to quartile three and quartile three to max, they would all have the same distance if the heights of the bars were exactly the same. But because most of the data is in the middle, the quartile one and quartile three are going to be close to the median. And the spread from the quartile one to the minimum, that's going to be more spread out because there's less data there. And the spread from quartile three to the max is it's going to be more spread out. So here is the box plot for this graph. And so notice that when things are squished together, the heights of the bars are taller. The median is in the center, and my whiskers are pretty long, which are telling me that the lower 25% of the data is kind of spread out, just like in this histogram. Let's look at the left graph. So this is what looks like a right skewed data set here. This histogram looks right skewed. And so that means the bulk of the data is towards the left part of the graph. And so that means that the median is going to be towards the left side. And quartile one, the minimum, and the median, because those bars are so tall, they're going to be kind of close together. And then between the median and quartile three, it's a little bit more spread out. And between quartile three and the max, it's even more spread out because there's not so much data there. And here's the histogram. Here's the box plot that's associated to this histogram. Notice that the median is right below the line that says median. And my tail, so my whisker for my box plot on the right is really long, which is telling me that this is right skewed. So when I have the whisker being very long, that's telling me it's more spread out there. So you can see how the top graph matches with the histogram. And so let me show you the other histogram for the last one. Look at the box plot for this histogram. It has a long left tail, and then where the left tail attaches to the box, that's quartile one. And then where the right tail attaches to the box, that's quartile three, and the line in the middle is the median. Notice that the spread between the median and quartile three is small compared to the median and quartile one. That's a little more spread out, which tells you there's less data there, which means that the bars are falling in height. And then the length of the tail is really long, and which means that the bars are falling even more in height. So I would say that this graph, if I was to just see the box plot, I would think the histogram would be left skewed. Okay, so something I would do in the homework is ask you to match which histogram is matched with which box plot. And so that's something to expect. Let's try another problem. Here I have two box plots, side-by-side box plots, and I want to answer some questions about it. So one I've labeled box plot X, and the other one I've labeled box plot Y. Okay, the first question is, to the nearest integer, what is the median of variable X? So maybe pause the video and write down what you think the median of variable X is. Okay, remember that the median in the box, we look for the line in the box, inside the box. And so in X, it looks like it's right in the center. And if I pull it all the way down, it looks like the median is about 40. If I wanted to find the median for Y, I would say it's about 31, somewhere around there. Okay, to the nearest integer, what is the third quartile of variable Y? So the data is organized from smallest to largest. You could see the data from 0, 10, 20, 30, 40, all the way to 110. So quartile 3 would be the right side of the end of the box. Okay? So on my box and on variable y, it looks like the end of the box happens around 52. So that would be the third quartile. Which variable has a has a larger IQR? So the IQR is the difference of quartile 3 and quartile 1. So that is finding the box with the largest width. And for Y, I think the IQR is about 52 minus 12, somewhere around there. While for box X, it looks like you would do about 45 minus 35. So definitely the box for variable Y is wider. So I would say variable Y has a larger IQR. Okay, let's describe the shape of the distributions for both variables. For variable X, the box part is in the middle, and it looks like the median is in the middle of the box. And the tails are a little bit longer than the box. I would think this histogram would be symmetric and maybe like a bell-shaped curve, like we saw in the last slide. There was a where the tails of the histogram are going down. If the whiskers were as wide as the box itself, I would think the the columns would be about the same height. But for this one, because the the whiskers are getting longer than the middle of the box, I believe the columns are going down, and this is symmetric. For box plot Y, I would say that this data is right skewed because the whisker length on the right, so the lower, the upper 25% of the data is really spread out, which means the bars are going down. And then when we head towards the right, things are getting more condensed. Sorry, this should say y is equal to right skewed. I got my left skewed and right skewed off, so I'll update that on the PowerPoint. Which variable do you expect to have a larger standard deviation? I would say variable y would have a larger standard deviation because the data overall is really spread out. And which variable has more data below the value 50? This one's a little tricky. So let's see where value 50 is. The value 50, if we look to see where it lives in the box plot y, it is between the median and quartile 3. That means somewhere between 50 and 75% of the data is below the number 50. While for variable x, the number 50 lives in the right tail. So the right tail is where between 75 and 100% of the data lives. So comparing those two, I would say that x has more data living below the value 50 than y, because 50 is above the 75% mark for the variable x, while 50 is below the 75% mark for variable y.